Ba, 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 ba.
Again, the request to move to the middle a little bit because we're expecting quite a number of latecomers after yesterday's conference dinner. Or be prepared to get up when people come down the stairs. So today I'm not the guy running around with the laptop, I hope. I may interrupt with some technical issues, but it won't be the computer, but perhaps like a minus sign mistake. So it's my great pleasure. Rest assured. So it's my great pleasure to introduce the first speaker of this morning's session, Stephen Carlip from the UC Davis. So he's worked on many topics in quantum gravity, and he has the distinctive ability to overview our field. He has written numerous review papers on, say, 3D quantum gravity, on space-time foam, on thermodynamics of black holes, and now he will review for us the causality in quantum gravity. We're very much looking forward to hearing about this. The floor is all yours.
Okay, thank you. So the organizers asked me to give a review on causality in quantum gravity, and I told them I would do my best. This is a tricky subject, partly because it's very broad, partly because it's not understood very well, and in particular for this talk because I don't understand it very well. So if you want to come up with questions to stump a speaker, this is your chance. So let's start at the very beginning. Back in kindergarten, when we first learn about relativity, we are taught that Einstein unified space and time into a single space-time. And of course, at some level, that's correct. But it's also potentially misleading, at least to kindergarteners, because space and time are still distinct, even if there isn't an absolute space or an absolute time. Space-time is characterized, at least classically, by a Lorentzian metric. And that means that the metric picks out light cones. Those determine local causality, which extends to a causal structure on the whole space-time. And that causal structure is really central to many, maybe even most of the important developments in general relativity in the past 50 years. Everything from singularity theorems and cosmic censorship to almost everything we know about black holes. After all, a black hole horizon is defined in terms of a causal structure. To asymptotic structures of asymptotically flat or de Sitter or anti-de Sitter spacetimes, or on a more ordinary, less mathematical level, the propagation of gravitational waves, all come around to causal structure. In fact, one can say a little bit more than that. There is some sense in which the causal structure is most of the space-time geometry. Specifically, if you have a causal space-time, think of that as just a space-time with no closed time-like curves, though there are some subtleties. But if you have a causal space-time, then there are some basic theorems that tell you that the topology and geometry are both completely determined by the causal structure and the volume element. Roughly speaking, the causal structure determines the metric up to a local scale factor. The volume element determines that scale factor. So depending on how you're counting, the causal structure is 9/10 of the metric, or if you want to factor out diffeomorphisms, it's still 5/6 of the metric. So this is a beautiful classical picture, and then, as usual, quantum mechanics comes along and spoils things. In particular, we expect that quantum fluctuations will blur out the causal structure by making light cones fuzzy. As far as I know, this idea was first suggested by Pauli in 1955 in a remark at a relativity conference, and very quickly taken up by Klein and Landau and others. Very soon after that, Deser and DeWitt started to look seriously at whether this fuzzing out of light cones, blurring of causal structure, what kind of effects that would have on quantum field theory. Now, there are a number of ways of looking at this. One first thing to notice is that gravity is attractive, so positive energy fluctuations make light converge. So they narrow light cones. This picture is actually not quite right. The tip of the dotted light cone should be the same as the tip of the outer light cone. But so positive energy fluctuations, one could argue, don't interfere with ordinary causality in the sense that they don't allow for travel faster than light. On the other hand, we're talking about quantum physics here, and in quantum field theory, field fluctuations can have negative energy as well. There are some kinds of average energy conditions that sometimes could be interpreted as saying that on the average, quantum fluctuations don't produce faster than light travel. But on the average is really not good enough for a question like that. You can also look at this in the context of effective field theory, where the effect of quantum fluctuations is abbreviated as the addition of higher derivative terms in the action. And in that case, there are some nice results about the signs of various coefficients that are required in order to prevent violations of causality. This puts some limitations on what kinds of effective field theories make sense have sensible ultraviolet completions. Again, though, this is basically a low energy consideration, and it is fairly easy to show in effective field theory that when you start to get to high energies, you get causality violation. For example, if you look at the effective field theory predictions for Shapiro time delay. In fact, one can say a little bit more than this about the effect of quantum fluctuations on causality and light cones. Quantum fluctuations of quantum fields are actually very highly non-Gaussian. They have a most fluctuations are negative. There is a strict lower limit, though, and there is an infinite positive energy tail that falls off more slowly than exponentially. Now, we don't know how to fully treat this in quantum mechanics, but if you look at these fluctuations and you approximate them as stochastic fluctuations, you can look at what they do to light cones. And the answer is related to this fat tail. You run into a phenomenon called gambler's ruin. The gambler's ruin theorem is basically the theorem that if you are betting against an opponent who has infinite resources, you always lose in the end, no matter how good the odds are for you. That's what happens here. Although most of the fluctuations are negative energy and actually bring light cones to a sort of equilibrium, sooner or later, one of these very high energy positive fluctuations is going to come along and collapse light cones. And in simple models, for instance, in 2 dimensions where this can be done exactly, you find that this happens, that for Planck scale fluctuations, this happens on the order of 100 times the Planck time. So quantum gravity, at least at the Planck scale, is certainly messing with causal structure. In fact, at least in principle, you can construct a superposition of different causal structures by hand. This is from a paper by Zick and collaborators. The basic idea is very simple. You start with 2 observers, Alice and Bob, who synchronize their clocks at some fixed initial time slice and agree that after a proper time, tau A, Bob will flash bulb, and after a proper time, I'm sorry, A is Alice. Alice will flash a flash bulb, and after time B, Bob will flash a flash bulb. These are nice diffeomorphism invariant statements. Now suppose that you put a very heavy mass next to Bob after this experiment has started. Then Alice will see Bob's laboratory time dilated, which means that she will see a delay before Bob flashes his flash bulb, which can be long enough that it puts event B, Bob's flash, to the past of event A, Alice's flash. Suppose you take the same mass and put it next to Alice, then you get the same result, except that the causal order is reversed. So now take the mass and put it into a superposition of a state where it's next to Alice and a state where it's next to Bob. That will give you a superposition of the causal orders of the 2 events, of the 2 flash bulbs going off. We can't do this in the lab yet, but as we've heard, the Vienna group and others are working very hard on putting significantly large masses in superpositions of positions at significant distances. This will come. So why is this bad? Well, the most basic answer is that it wrecks quantum field theory. One of the most fundamental axioms of quantum field theory is microcausality, which is the statement that if you have 2 operators whose support lies on space-like separated points, then they commute. They can't affect each other. And this is really part of the fundamental basis for quantum field theory as we understand it. For example, this is the key ingredient that goes into the derivation of the analyticity properties of the scattering matrix. But if we don't know whether points x and x prime are space-like separated or not, or if we have a superposition of space-times where they're space-like separated in some and not in others, we basically just don't know how to do quantum field theory in a setting like that. And to the extent that we can think of quantum gravity as a fancy quantum field theory, this is part of the reason that we don't know how to do quantum gravity. This fuzzing out of causality is also very closely related to what are commonly called the problems of time, as discussed in Kiefer's talk. For example, it's commonly said that in order to make sense of probabilities in a quantum theory of gravity, you have to normalize them, which means normalizing them at a fixed time. You want to say that there's a probability of 1 that your electron is somewhere in the universe at a fixed time, not that it's ever somewhere in the universe. But if you think about this, the reason a fixed time is important is precisely because of causality. It's because you want to normalize probabilities on a hypersurface in which you know that the electron won't be there twice. If you don't understand causality, then you don't understand the first step even towards what it means by saying at a fixed time. And of course, that also means that you don't understand what unitarity means, because unitarity is a description of what happens when you move from one fixed time to another fixed time. So again, we don't know how to do quantum mechanics. So that's why this might be bad, but there are other reasons that it might be good. And these go back again to Pauli in 1955. If you look at the divergences in ordinary quantum field theory, we usually think of those as coming from infinite momentum exchanges. But if you translate that back into position space, the divergences come from fields at points that are null separated. And so if your light cones are fuzzed out, then maybe those divergences go away. This was first taken up by DeWitt in the early 1960s and then worked on by a whole series of other physicists who basically, from first principles in ordinary quantum field theory, said, let's look at a divergent diagram and then sum up an infinite number of diagrams that include gravitons. And they found that for certain infinite series of diagrams, the divergences of the individual diagrams disappeared, and you did get finite results. Now, this is an intriguing idea. It more or less faded out of sight because it's one thing to be able to show this for some particular subclass of Feynman diagrams, but you really need to know it for all Feynman diagrams. And of course, we don't know how to do that. Richard Woodard has pointed out that the cancellation here that these people have seen involves cancellation between different orders in the perturbation expansion, and what might be needed is some systematic reorganization of perturbation theory in quantum gravity, but we don't know how to do that. So other people have approached this more phenomenologically. You can just take your propagator in quantum field theory and by hand stick in some fuzziness, either stick in a minimum length. The first expression there is from a paper by Padmanabhan, or smear out the propagator with some smearing function f. The second expression is from a paper by Ohanian. There have been a whole series of phenomenological models like this, and they all give more or less the same result, that in fact fuzzy light cones might very well get rid of divergences in quantum field theory. There are a few other reasons that you might like the idea of some sort of mild breaking of causality in quantum gravity. For one thing, it allows topology change, which, depending on your personal point of view, might be a good thing or a bad thing. But there are some basic theorems that essentially say that if you have a Lorentzian metric that is causal, if you have a Lorentzian metric, then change in spatial topology requires either singularities in the metric or closed time-like curves, that is, violations of causality. So if you want to allow such changes, the easy way to do that is to allow violations of causality. This might be important in the answer to the problem of the question of black hole information loss, where some of the recent work gives a very important role to wormholes and other forms of non-locality, which in turn require this breakdown of causality. Also, there might be observational consequences. This at least gives us something that we can look for. For example, in loss of coherence of starlight and breakdown of interference patterns from light from distant galaxies. I'll come back to that a little bit at the end. So suppose that you believe this, that quantum gravity somehow allows superpositions of different causal orders, or the path integral includes paths with different causal orders, or quantum fluctuations mean that your light cones are not a fixed structure. One of the first questions you have to ask is whether it's even possible to do quantum mechanics in that setting. And certainly you can't quite do quantum mechanics as we ordinarily do, because in ordinary quantum mechanics, the way you treat two systems that are space-like separated is very different from the way you treat two systems that are time-like separated. If you have two space-like separated systems and you want to write a wave function, you write down a product wave function or a superposition of product wave functions, but wave functions on a product of two Hilbert spaces. If you have two systems that are time-like separated, that is, if you have a single system at one time and then another, you write that in terms of a single Hilbert space and some operator that tells you how to get from your initial time to your final time. So there's been a lot of work. This is one of the areas where I'm very definitely not an expert, so this is an outsider's summary of this. There's been a lot of work, starting with Hardy in 2005, looking for reformulations of perhaps slightly generalized quantum mechanics in which you treat space-like and time-like separated systems on an equal status, what's sometimes called causally neutral quantum mechanics. There's also been work from more within the quantum gravity community, for instance, by Eckel on the path integral version of this kind of idea, the general boundary formulation. The answer is that it can be done. There are a number of different approaches, but that are, I am told by experts, more or less equivalent, that allow you to write down this slight generalization that reduces to ordinary quantum mechanics when you have a single causal order. When you do this, you find that there is an analogy to Bell's theorem, that there are certain inequalities that that must be obeyed if you have a fixed causal order but that can be violated if you can have a superposition of causal orders. Now the way that I've stated this, I haven't referred to gravity at all. And in fact, there are proposals and even claims of implementation of this kind of structure in the laboratory, where you simply have some qubit that can go through 2 gates, and you can choose to have it go first through gate 1 and then gate 2, or first gate 2 and then gate 1. You can put a quantum control system that then allows you to put a superposition of those orders. So that looks sort of like a superposition of causal orders. This is a little mysterious, though, because this is all happening in a lab in a very nearly flat space-time where there is an outside definition of causal order that doesn't depend on how you set up your quantum system. And my understanding is that there's some controversy about this, but there are claims that look at least completely plausible to me, for instance, by Villacini and Renner, that say that you cannot, in fact, set up this kind of superposition as a superposition of pure states, at least, in the laboratory. This is without gravity, though, and with gravity, presumably there is nothing to prevent something like this from happening. So this is still somewhat of an open question, as I understand it. There's still room for surprises. For instance, there is this beautiful thought experiment by Balencia, Wald, and collaborators that looks as if it allows you to use gravity to violate causality. The basic idea is simply that Alice takes a mass, puts it into a superposition of positions, and Bob, at a space-like separation, decides either to measure the gravitational field, which would then determine which of those positions the mass was in, or decides not to, in which case Alice's particle remains in the superposition and she can recombine the paths and look for interference. It turns out that there is a conspiracy of 2 quantum gravitational effects. On the one hand, there is the quantized emission of gravitons from Alice's particle as she moves them apart or together. And on the other hand, there's an uncertainty in the maximum precision that Bob can make his measurements from gravitational fluctuations of the space-time. These 2 things together combine to just barely prevent this kind of experiment from violating causality. So there's something deep in quantum gravity that really likes causality, but I don't think it's understood what that is. So now let me turn to a few specific examples of how causality comes in, or causal structure comes in different approaches to quantum gravity. The starting point is causal set theory, because that's an approach which is fundamentally built on causality. So the idea here is that if you want a discrete model of space-time and you want to start with causality, with these theorems about the causal structure plus volume determining space-time, then there's a natural form of discretization, which is to start with a discrete set of points, but points that have a causal order, where x precedes y mathematically is interpreted as x is to the causal past of y. And then you add two features. You add a feature of no closed time-like curves. There are various ways of doing this. The simplest one for me to understand is to simply require that no point is in its own past. And then you put in a discreteness requirement, which Samadhi Surya talked about, gave a little demonstration of in her talk. You simply say that the causal diamond, the future of one event intersected with the past of another, always has at most a finite number of points in it. So that gives you the basis for causal set theory. And if you start with a space-time and then use this picture to form a discretization, a discrete causal set, then we understand the resulting topology and geometry fairly well. That is, we understand the causal set determines some discretization scale, but at distances above that scale, we understand reasonably well how from the causal set to reconstruct the volume, the dimension of the space-time, the volume, the curvature, the coarse-grained topology, as well as nice things like D'Alembertians and Green's functions. If, on the other hand, we want to think of causal sets as being fundamental, it looks like a complete disaster. Almost all causal sets, and I mean this in the strong mathematical sense, at least in the limit that the size of the causal set goes to infinity, almost all causal sets are these peculiar things called Kleitman-Rothschild orders, which have only 3 moments of time. That is, if you start at one point, you can go at most 2 steps to the future before the causal set ends. That's not our universe. It's not a space-time at all. You might hope that those are some sort of weird exception, but if they're not, if you throw those out by hand, almost all remaining causal sets have only 2 moments of time. You throw those out, almost all of the remaining causal sets have only 4 moments of time, and so on. So the reason that I'm mentioning this is that a recent result by Peter Carlip, Samadhi Surya, and me, which is being written up almost as I speak, we've shown that if you use the standard Einstein-Hilbert action with the appropriate discretization to make sense for causal sets, then the path integral, or strictly speaking, the path sum, very strongly suppresses these non-space-time-like layered causal sets. Very strongly means by a factor of 2 to the minus n squared, where n is the number of points in the causal set. So for a region of a cubic centimeter times 1 nanosecond, that's a factor of 2 to the minus 10 to the 260 something. So that's pretty serious suppression. So let me emphasize, though, and I'll return to this later, that a classical causal set has this idea of classical causality built in. But if you're looking at a path integral or a superposition of causal sets, you get causal sets with different causal orders. There's nothing different here for causal set theory than what I was saying very generally for quantum gravity. One thing I'll mention in passing, again, this is something that I'm not an expert on, but there is a nice argument by Bianchi and Martin Dussaud that if you have a simplicial complex or a spin foam, that naturally contains a causal set structure from looking at the one skeleton, that is just looking at the lines connecting the interiors of neighboring simplices. That comes with a natural direction. There are nice consistency conditions that make it into a good causal order. And this has interesting implications that I don't understand for spin foam theory. Now, let me briefly mention one other particular case where causal structure has been important and interesting in a very different context, which is holography, and in particular, the ADS-CFT correspondence. So in the ADS-CFT correspondence, you have a boundary at infinity that has an ordinary quantum field theory with no fluctuations of the metric, and so with an ordinary fixed causal structure. And that quantum field theory is supposed to be equivalent to a theory of quantum gravity in the interior of space-time, of the asymptotically anti-de Sitter space-time, so in the bulk. So this leads to interesting threats of contradictions. You're supposed to be able to get the quantum field theory at the boundary as a limit of various quantities in the bulk, quantum gravitational quantities. But in the bulk, you can include, and in fact you have to include, metrics in which points that are space-like separated at the boundary can connect to each other along time-like curves in the bulk. It's easy to write down metrics that do this, and there's no reason that they should be excluded from the bulk path integral. So this looks as if boundary causality is inconsistent with the bulk theory. So there's been a very nice analysis of this by Gary Horowitz and his students, who point out a kind of subtle detail, but that turns out to make a huge amount of difference. So first of all, this condition of boundary causality is very strong, because it says not only that the commutator of two space-like separated operators at the boundary has to be 0, but that if that commutator appears in an arbitrary correlation function with any number of other operators, it still has to give 0. That seems to be a very hard condition to obey. But what these authors pointed out is that writing a commutator as a path integral is tricky, because path integrals automatically give you time-ordered products of operators. And so if you have operators that are time-like separated, the path integral will give you the product of those operators in a particular order. And you have to do something funny to get the out-of-order product in order to define a commutator. Specifically, you have to sort of integrate forward in time and then backward and then forward again. And that changes the manifold that you're defining your path integral over into something that they call a time fold, where it folds around at some time. And what they showed is by carefully analyzing the boundary conditions for time folds, that the contradiction goes away, that in fact you can't connect the boundary points through the bulk in a way that gives you a non-zero expectation value for these commutators. So that's another interesting place where quantum gravity seems to conspire to give you causality where it would seem to not be there. So a couple of brief comments about causal structure. Elsewhere, we can look at the general path integral. And as Bianca Dittrich told us in a really beautiful talk at the beginning of the conference, there is a lot of progress now in trying to understand path integrals using Lorentzian metrics, so in ways that at least admit that there is a causal structure. Now, there's an interesting old issue here that, as far as I know, remains unresolved that goes back to Claudio Teitelbaum's thesis. Suppose that you look at a Lorentzian path integral in Hamiltonian form. So the ordinary Einstein-Hilbert action in Hamiltonian form looks like pi q dot, the usual pq dot term, plus some constraints. And let's look in particular at the Hamiltonian constraint, which is supposed to be at least the equivalent of the generator of time reparameterization, sort of diffeomorphisms involving the time direction. So if you look at this path integral, if you integrate n, the lapse function, from minus infinity to infinity, that gives you a delta function of the constraint. That's nice. That tells you that the only paths that come into the path integral are paths that obey this constraint. That's good. The problem is that the lapse function geometrically is the thing that defines proper time intervals, that d tau is roughly just n dt, where t is your some standard time coordinate you've chosen at the beginning. And if n can come in with an arbitrary sign, then you can have paths that move forward and then back and then forward. In other words, you have paths in the path integral that very obviously violate any sensible meaning of causality, that very specifically move backwards in time. There's an easy alternative to this, which is to allow the lapse function only to run from 0 to infinity. That means that you're only looking at paths that are moving forward in time. If you do that, though, then the integral over the lapse function doesn't give you a delta function anymore. And while configurations that don't satisfy the constraints are suppressed, they're only suppressed in the same way that any other configurations that aren't classical solutions are suppressed. So this is a mystery. Do we want to not impose causality but impose the constraints strongly? Do we want to only impose the constraints approximately but keep causality? I think the answer is basically unresolved. So we've also seen these issues of causality come up in other contexts already in this conference, in the current attempts to transfer what we know about asymptotic safety to a Lorentzian setting, where there were some interesting results in the parallel session about state dependence of the renormalization group flow in the infrared if you have a Lorentzian renormalization group. Some very nice work on the Lorentzian spectral function. There is causality in causal dynamical triangulations, which I'm not going to try to say anything about because that, I believe, is the subject of the next talk. So let me conclude. So when my son was in elementary school, he decided that a good working definition of science was that science is a state of confusion. This is not a bad definition, because the purpose of science is to discover new things, and you're not going to discover anything new if you aren't confused about what you think you already know. So that's where I think we are in terms of causal structure in quantum gravity. There is a lot of interesting work on ways that individual classical spacetimes or classical-like spacetimes in a path integral or a superposition can be causal, how causality can be put in explicitly in everything from causal sets to boundary unitarity. Very interesting work in that area. But none of this answers the question of why superpositions of causal orders aren't completely obvious around us. Causal order is something that seems pretty physically fundamental. But as I've said, there is nothing obvious that prevents you from having superpositions of causal order or having fluctuations in causal structure. And so the question is why this is so strongly suppressed in observation. I don't know the answer to that. Well, I'm confused. And I'm not sure that anybody does. There are certainly arguments that say that, there are certainly settings in which there are good arguments that say that violations of some background causal order can be suppressed in the path integral. Dietrich and Asante have talked about that in the discrete context, for instance. But it seems to me that it takes awfully strong suppression for everything that we know about classical general relativity to work so well. So I want to leave this in part as a challenge to the quantum gravity phenomenologists. There has been a lot of work about how we would see things like violations in Lorentz invariance. There has been, I think, less work on specifically how superpositions of causal order might show up observationally. And perhaps it's just that my intuition is wrong and that these are very hard to see, even though they occur in principle. But I think that this is something worth exploring in much more detail. And so on that confused note, I will stop. Thank you.
Thank you, Steve, for this beautifully clear review of our confusion. So I think you've also provoked quite a bit of discussion, and we have time for several questions. Let's start here in the back with Christoph.
The causal structure is a property of the metric, just like the rest of geometry. Now, of course, if you do a functional integral over metrics, you have obviously an integral over very different causal structures. So the superposition of causal structures is there whenever you have a functional integral over the metric. But the question is, where could you observe violations? Let me just have a simple picture. You know, at the end, you have a functional integral, you compute the effective action, you have field equations, and if you find, and the field equations are, of course, for the expectation value of the metric. So if the field equation leads to a metric that has a reasonable causal structure, then it's very hard to see where you could observe possible violations, because you would have to go beyond the expectation value of the metric. You would go to fluctuations, higher order correlation functions, or something like that. But it seems to me that when you have a situation where the solution of your field equations has an acceptable causal structure, then you are, for most purposes, more or less done.
So the question is how exactly what most purposes means in this context. And yeah, I agree. Now, there are certainly situations in principle in which you can have macroscopic superpositions of causal structures.
Chris, please take the microphone if you want to comment.
All that is, of course, if you think about a functional integral, you can, of course, once you have the quantum effective action, describe all observations by correlation functions.
Right.
Even, you know, superpositions of atoms, of clocks, and so on. It's all, at the end, goes back to correlation functions. So the question is, in what type of correlation functions could one observe violations of the causal structure if one has already a situation where the expectation value of the metric has a very acceptable causal structure? And that is not obvious to me.
Yeah. I agree that it's not obvious, but it is, I guess the only thing I would add to that is that the fact that causality is observed to play, the fact that causality plays such an important role in so many parts of classical general relativity suggests to me that even fairly subtle violations ought to be visible. I mean, a standard example would be that if you have light coming from a distant galaxy that's traveling through a space-time with a superposition of metrics, you should expect a superposition in the times of arrival of photons. And certainly you can look at the expectation value and get a nice answer that agrees with what we see. But you can then ask, are there interference effects, or in this case, blurring of interference effects, because of the fact that the photons are traveling in a superposition of classical metrics with different causal structures. As I said, I don't know the answer to this. I think it's something that's begging for more careful analysis.
Okay. So maybe I can shortly comment on this question. So the situations like this on the slide, the gravitational quantum switch. So of course, like the example with the Earth is just a thought experiment, so it's not something that we aim at realizing anytime soon in a laboratory. But in principle, this could be realized by putting a mass in a quantum superposition, like the ones that Markus Aspelmayer has in his lab. And that is exactly a situation in which you cannot approximate the stress energy tensor with its expectation value. So basically, the situation that would realize, so okay, so if we want to take an effective field theory description of that type of situation, we would have to linearize Einstein's equations, and then we have a quantum perturbation on top of, say, Minkowski, and then the source is prepared in a quantum superposition of two macroscopically distinguishable states. That in quantum theory, that means that they're orthogonal one to the other. And then, basically, you would have for, okay, so we also have a paper with Ling Chin and with Carlo Rovelli, where we have exactly this, the description in linearized quantum gravity of this situation. And then what you assume is basically for each classical position of the sorts, then you effectively, the state of the sorts is an eigenstate of the current of the gravitational field, and you can do exactly the same for electromagnetism. And then you superpose these two solutions. So now, coming to the switch, this is of course, so the element that you take from this description is that you can linearly superpose these two solutions and that you can effectively treat the gravitational field as classical in each amplitude of the superposition. And then you are able to superpose the paths of the two photons for each classical position of the mass. Then there is another whole story that comes from a more quantum information perspective, that is the process matrix formulation in which this gravitational quantum switch is formulated, that is instead something that does not require starting with space-time at all, as you actually mentioned in your talk. And then it's just about logical compatibility of signaling relations between two laboratories, A and B, in which you can perform local operations. And then this would be a structure that allows for superposition of causal orders without actually ever violating any causality principle. So you basically, just by imposing conditions on the probabilities, you can rule out logical paradoxes. So, and you don't have to do that by hand. So this is just to clarify a bit the framework in which this is, this can be understood. But thank you for your talk. I really enjoyed that.
Yeah. Can I just?
Yes, so this is a very nice discussion. Perhaps I can ask whether there is a question from a different corner of the room? Or we can just continue this discussion. It's fine with me. We're a democracy here. So yes, go ahead.
I just want to add a quick comment. Is that the causality, the definition of event in relativistic community and in quantum information is actually different. So here, this is pointed out very in a paper by Villassini and Renato Renner. They point out very clearly that so for causal set and for gravity, quantum gravity, we treat a point on the manifold as an event. But here, like in this paper in the gravitational switch, each event is like a local intervention relative to some reference frame for the local laboratory. So I think it's like very important to discuss about the indefinite causality when we distinguish these two concepts.
So do we have any questions from the chat, perhaps? No? Okay, very good. We can have a last. Okay, go ahead.
Just to answer this question, let's be a bit more precise. I mean, the field equation for the mean value of the metric has on the right side the mean value of the energy momentum tensor. This is just an identity, you cannot change it. So you can now say that this is not enough, but then you have to go to correlation functions and you have to tell me which type of higher correlation functions you are observing in your experiment that goes beyond that. And then one can judge if one could expect there a possible violation of causality or not, or something like that. But I think it has to be phrased in this way. Otherwise, it's too, just to say the energy momentum tensor is a superposition. Well, you have to think what you do. I mean, the field equations are for expectation values, and that's definitely the expectation value of the energy momentum tensor on the right-hand side. That's just a mathematical identity if you go to functional integrals. And you have to reformulate things into higher correlation functions, 2-point functions, 3-point functions, I do not know, in order to be able to judge really what this, for me at least, what this experiment could probably tell us.
Okay, so thank you very much for this comment. Maybe, do you want to comment further on this? No?
No,
Okay.
I agree with, I don't think there's been any contradiction in what people have said, and as far as I can tell, I agree with all of it.
Okay, so let's give Steve another warm round of applause. Let me switch to speaker. Quantum switch. Very good.
That thing is called.
It's magic. No confusion there. Okay, so our next speaker of this causality session this morning is Jan Ambjorn from the Niels Bohr Institute in Copenhagen, but luckily we can also call him a local here. So Jan is known for his many works in quantum field theory and quantum gravity, but perhaps most for being an initiator of the dynamical triangulation approach, starting in string theory, but later also in the gravitational path integral. Causality entered the business with the introduction of CDT together with Renate, and I'm happy that he agreed to give this focus talk with an update on the CDT approach to quantum gravity. Jan, please take the floor.
I'd like to thank the organizers for giving me the opportunity to present this work. Yes, okay. Yeah, so what I will discuss today is the search for an ultraviolet fixed point using the lattice theory called dynamical triangulations. Well, the main goal for quantum gravity, at least in my formative years in the 70s and 80s, that was to obtain a background geometry, preferably the one we observe, and to be able to study the fluctuations around this background geometry. And what the four-dimensional CDT offers to us is a non-perturbative quantum field theory definition of quantum gravity, or I should say some kind of quantum geometry. It's our task to prove that it eventually can be viewed as quantum gravity. It's a background independent formulation, and what it also offers to us, as I will explain here, is an emergent background geometry and the possibility to study the quantum fluctuations around this emergent background geometry. So pretty good from this point of view. But of course there are problems for any theory of quantum gravity, and also for a lattice theory of quantum gravity. So I listed some of them here. Well, first of all, one should actually define this theory, and what we want to do, we want to have a real mathematical definition where one might, like in the path integral in lattice quantum field theory, where you have a functional integral which is well defined, but of course it's your task to prove that you can take some kind of continuum limit of it. And we have to face the non-renormal stability of quantum gravity. And we have to provide evidence, as I said, of a continuum limit, and that this continuum limit has the desired properties of whatever theory we think about. And well, we also have to face the possibility that there might not exist a continuum quantum field theory of gravity definable at all scales. Of course, there exists an effective quantum field theory, but it might not exist at all scales. So if that is the case, can a lattice theory be of any use? I will not have real time to discuss point 4, which is quite interesting, I think. So I will just answer this in one word: yes. And I will mainly discuss point 1, 2, and 3. So how to define the quantum theory? Well, we have the classical action of gravity, and we can define the path integral via the quantum theory via the path integral. And the path integral is wonderful. I mean, this formula is oops. So yeah, this is a wonderful formula. Any classical action, you put it in here, and here's my quantum theory. But of course, the problem is the devil is in the detail, of course, of defining this. And in this case, what is the precise meaning of this integral here over geometries, as I've written it here? So classical gravity refers to a manifold with a metric and Lorentzian signature. If you get this perverse idea to rotate to Euclidean signature, then anyway it refers to smooth Riemannian manifolds. But we know even in quantum mechanics, I mean, the path integral is not all smooth paths. I mean, we have to integrate over all kind of fractal paths, and they're continuous. So it seems that as a minimum, we would have in any path integral to integrate over continuous geometries. And this is a very unwildly concept, actually. Also, what should we actually include in the integration, or should we integrate over different manifolds? Well, in string theory, we are clearly forced to integrate over different manifolds because this string can split up and join and change topology and so on. But in quantum gravity, as such, it is less clear. And CDT, which I'll talk about here, it takes a minimalistic view on these problems. One fixes the manifold. I will only here discuss the situation where the manifold is R, which is the direction of time, and S3, which is a compact space. We will actually use, to define the path integral, we will use a subset of continuous geometries. In fact, a subset of what is called piecewise linear geometries that can just be constructed by gluing together identical building blocks for synthesis. So the hope is that these are dense in a set of continuous geometries. And well, this has basically been proven in 2D that this is true. If you have the right measure, I mean, of course, this measure has to be quite coarse, some Gromov-Hausdorff measure of some fancy mathematical measure of this, but it is, that's basically the hope. So inspired by canonical quantization, we will assume a Lorentzian signature from the outset, a hyperbolic spacetime, and a time foliation. And then we triangulate this using the building blocks. And then for the action, we should use some action there, and we put in the Radje action for piecewise linear manifolds, because this is a very nice action in the sense that it doesn't need coordinates. Once you know the lengths of the links in the triangulation, which is a kind of diffeomorphism invariant concept, then you know the geometry. You can reconstruct the geometry. What is a somewhat kind of remarkable aspect is that if we build up now these CTT triangulations, and I've tried to illustrate them here. You have the time slices here. I'm reading R3, it should really be S3, but this is an old figure, so I didn't change it, okay. So we have triangulated the spatial slices here with tetrahedra glued together in all possible ways, compatible with the topology of S3. And then we connect them, the slab in between, we fill it out with force synthesis in some specific way. The one tetrahedra here is connected to a point here, a triangle here is connected to a link here, such that we get force synthesis in between. And then we glue these together such that in the slab in between, the topology is the same as the spatial topology. And we sum over all of these, and what we use is this Radje action in the path integral. But the remarkable fact is that we can now rotate, for each of these kind of Lorentzian geometries, we can actually kind of rotate them to an Euclidean geometry, where each building block now is a force simplex, where all links have the same length A. And this length is then going to play the role of we imagine, as a diffeomorphism invariant ultraviolet cutoff of our theory. Exactly like the lattice length of a link plays this role in ordinary lattice theories. And another remarkable feature is that if we take this Radboud action, which in general is very complicated if you have some kind of triangulation, if you use identical building blocks, then it is simplifying in a dramatic way. So now let me have a four-dimensional triangulation T, and let the number of building blocks be N4, and the number of triangles in this triangulation be N2, and the number of vertices be N0. And then the action is just this expression here. K2, some dimensionless coupling comes times N2 plus K4 times N4, where K2 and K4 are related to the continuum gravitational coupling constant and cosmological constant in this way here. And you can exchange this. There are some thing called Dense-Somerville relations between the number of subsimplices in a triangulation, which means that you can relate this to this thing here, where you exchange K2 with K0. So we have usually done this, which is a mistake, I now realize, but that's too late because we have published many articles where you use K0, but nevertheless, that's how it is. So the action is amazingly simple. And we kind of generalize this action. So you see that it's just linear in the number of these building blocks. And we then, in a Wilsonian spirit, we kind of generalized it to a slightly more general expression where we, so when you go back and you see these building blocks, there are two kinds of building blocks. You can say when we have this time foliation, namely this building block where we connect here, and this kind of building blocks. These are the two different ones, and if we can put in a different weight for these, we don't have really a precise kind of geometric interpretation of this, but in a Wilsonian sense, this is a natural generalization, and then it can be written like this. Instead of these two coupling constants, we keep the K4 here, but then we have a delta for some ratio between these. So we have three coupling constants, K0, delta, and K4 in our theory. And then we have our path integral. This is the continuum path integral. Now we replace it by our Lorentzian path integral, where we sum over these Lorentzian triangulations. But for each of these guys, we can make a rotation to Euclidean space. And then we have what we call the Euclidean CDT path integral, which can now be written as a sum of all triangulations. There is some combinatorial weight here, which I will not discuss. Then there's the action, and the action is very simple. It only contains N2 and N4. So we can split the sum over all triangulations in a summation over N2 and N4, and then the number of these triangulations. So here's a remarkable fact that the partition function of quantum gravity is just a generating function of the number of abstract triangulations with a given number of N4 simplices and N2 simplices. So it is purely geometric, kind of combinatoric. And that is actually what allowed this whole industry of two-dimensional quantum gravity, Liouville theory, and so on, to take off and be solved exactly. This was because in 2D you could count this number here. Unfortunately, in 4D we cannot really count it, so we have to rely on computer simulations to count it for us. But that's basically a kind of quantum gravity. You can say this must be much too simple. But my point of view is the opposite. It's wonderful that it's so simple, and it gives us a hope that one day we will understand kind of quantum gravity, four-dimensional quantum gravity, in a much more profound and simple way. But now we have to face the fact that it is a kind of the theory is not renormalizable. Well, it's easy to make it a renormalizable theory. We can just add an R-squared term. This was already done by Stelle in '77. This makes the theory asymptotically free. The problem was, as already have been discussed in other talks, the problem with unitarity. So another route was taken by the asymptotic safety scenario by Weinberg and also other people. And it has been implemented via the functional randomization group approach. Here one investigates whether one can find a non-perturbative ultraviolet fixed point in a Wilsonian formulated theory of quantum gravity. And so far, one should say that this functional randomization group has provided support for this idea, that such a scenario is satisfied. So four-dimensional CDT has a reflection positive transfer matrix. One can prove that. And in lattice series, having such a reflection positive transfer matrix guarantees that if a continuum limit exists, then the corresponding theory is unitary. So probably whatever CDT is in the continuum limit, it would not have the problem of non-unitarity. So that's a good thing. And lattice field theories as such are well suited to investigate fixed points and the corresponding continuum limits. So thus it seems, on the surface at least, that CDT is ideally suited to address the asymptotic safety scenario. Let me spend a little bit of time, although I don't have it, on trying to recall how this is done in standard lattice gauge theory. So actually here I will repeat a little bit of what Kai Christoph already told us, but I guess it never harms to repeat the wisdom words of Christoph. So I will. So he actually said a number of these things, but let me repeat it here in the context which is suited for our discussion. So the prime example of a lattice theory where you can take the continuum limit is the asymptotically free theory. Yang-Mills theory is the best example of that. So one just has one bare coupling constant, let's call it G0. From perturbation theory, we know that there is an ultraviolet fixed point when G is equal to 0, and one can calculate the beta function either on the lattice by lattice perturbation theory or in the continuum. Anyway, it's given like this, where A is the lattice spacing. So this is the ultraviolet cutoff. And of course, to the first approximation here, one can just solve for A, and you see that when G goes to 0, A goes to 0. So this is how we can take the continuum limit. And in actual lattice simulations, when one puts things on and one wants to address some physics, like measuring the strength tension, the glue balls, or if you have a more complicated theory where we also include fermions, then the masses of pions and whatever, one just kind of measure this dimensionless mass, which one has to, of course, to define in the lattice context. This has to be equal to the physical mass times the cutoff, simply for dimensional reasons, that one has a relation like this. This exists when the cutoff is going to 0, and because of this relation, then we know exactly what we should measure if such a continuum mass exists. We should measure, as a function of G0, a behavior like this. And this is done. This is beautiful. It's done on the lattice, and you can see this. And of course, this formula is the famous dimensional transmutation, where the cutoff is exchanged for a non-perturbative scale, lambda Yang-Mills. So here, everything is clear. Now let us turn to a non-Gaussian fixed point. And as a nice example is the phi to the fourth theory. So here I've written down the Lagrangian for phi to the fourth theory. Of course, you can put this on the lattice, so let's imagine that we have done this. You can define a renormalized coupling constant in terms of this bare theory. I will not go into the details of this. There are many definitions, but anyway, there's a specific definition such that for any value of m0 and lambda, you can calculate this thing. So now we are on the lattice, and let's take the coupling constants, both this and this, to 0. Then we are here. This is just a free field theory. Both on the lattice, you can define it, and in the continuum, of course, this is free field theory. This operator is a relevant operator. When you move out here, you will get a mass added to your theory. And you can approach this point here by tuning the mass to 0 in such a way that in the continuum theory, you get a free massive theory, not a massless theory. But on the lattice, this has, and also in the continuum, there is a unbroken phase where the expectation value of phi is 0, and there's a broken phase when this m is negative. Along this line, the correlation length is infinite. So this is a second order phase transition if you view it as a statistical system, and the correlation length is infinite. And of course, the question one asked in the old days was that, here it was clear that we didn't get an interacting field theory when we took the continuum limit, but we would like to have an interacting field theory here. Anyway, this appears more or less in the standard model. So it wouldn't be nice to have an interacting field theory which exists at all scales. But this requires that there is an ultraviolet fixed point here. So how do we find this ultraviolet fixed point? Well, what is what is physically characterizing this ultraviolet fixed point? Well, this is the fact that this renormalized coupling constant should exist when we take the lattice spacing to 0. So now let's take an arbitrary point here in the m0 lambda space. Here, we can then use our definition to calculate this value. So it has a certain value. At this point, it will have a different value, and at a third value here. But then we follow the path where we change these bare coupling constants such that this renormalized one stays fixed. And then we are guided automatically to the ultraviolet fixed point. So here we will get also to the ultraviolet fixed point, and here also, depending on where we start and following this track, I mean, the kind of renormalized coupling constant will have a different value, but it will exist and be non-zero. So we would have an interacting theory here, and you can also scale the mass to a given value at some point. So this would exactly be an interacting phi to the fourth theory. So this is beautiful, except that what happens when if you would do the calculations is that you start out in one point here, and then you follow this path of constant renormalized coupling constant, but you never reach this point here. So the conclusion was that there is no ultraviolet fixed point. So there's only this infrared fixed point. And if you, the correlation length along this line goes to infinity when we reach this point, and here it never goes to infinity. So we cannot, we can define a renormalized coupling constant, but we cannot take the lattice spacing to 0. So the ultraviolet limit doesn't exist, even if there's an effective theory with a kind of renormalized coupling constant. So that is the story. And here I've drawn the beta function if there has been an ultraviolet fixed point. So here it starts out with the infrared fixed point, and then it will cross here. So this was what kind of Christoph also explained to us. It will cross here at some fixed point with some slope, and at this slope you can just kind of linearize the theory, and then you put in to the normalization beta function group, and you can integrate it, and you find that the lattice spacing, it goes to 0 when the derivative of this function is negative. So this negative, it means that it's an ultraviolet fixed point. And then we can define a continuum. So that is the story. So let's go to CDT. So what is the story there? Well, here's the phase diagram for CDT. Determined by Monte Carlo simulations, so it's actually a complicated phase diagram. I mean, the red lines are second order transitions. So this is where some potential correlation length could be infinity. We haven't really defined a correlation length, and that's a kind of problem, an annoying problem, I would say, but that's how it is. But we would like to so I've drawn the phase diagram here, but only with two coupling constants. So the K4 multiplying this N4 is not really in our phase diagram, because we can only do the computer simulations with fixed N4. So this doesn't appear as an effective coupling constant. We can simulate with different N4s, but during the simulations, somehow our measurements are all done with fixed N4. So this is just technical reasons, but that's how it is. So this phase is not interesting, and this phase is not interesting from a continuum point of view, as I will show to you. But this phase, which we have called de Sitter phase, for reasons I will explain in a second, is very interesting. And then this phase here is not so interesting, but still interesting because it appears at the phase transition line here. And in particular, this phase transition line has a very simple interpretation. So here we imagine, and as far as we can judge, this is the case, that these spatial slices are homogeneous and isotropic. But when we cross this line, this homogeneity is broken. So it's a symmetry breaking transition, exactly as the phi to the fourth transition I told you. And then it would be very nice if there was an ultraviolet fixed point somewhere, maybe here. This almost screams to us that if there is an ultraviolet fixed point, it should be here. And I should also say that I mean, this phase, this means that there would be an ultraviolet short distance physics associated with this breaking of symmetry. And well, when you think about cosmology and short distance, then it could have, if it turned out to be true, implications for cosmology. That the nature of this phase transition is breaking symmetry, breaking homogeneity and isotropy. And that would then propagate all the time today with the formation of galaxies and so on. Of course, one should really define what it means to be homogeneous and isotropic in a quantum space-time. So Laurel and Silva has actually discussed this recently. I have no time to go into this. But let us take a short look at the structure of the geometries that we see in the computer. So I've dropped here the delta for clarity and just the bare coupling constant K0, which is formally proportional to 1 over G, the gravitation coupling constant. So when this bare coupling constant is small, there is no space-time. Time collapses to just a single slice here. And when it is very large, there's also no interesting space-time because all spatial slices are basically not correlated at all. They just fluctuate randomly. But in between, a blob is formed, and in the de Sitter space, this scales as a real four-dimensional. So if we have N4 as a measure of the total 4 volume, then the height of this scales as N4 to 3/4, and the width of this scales like N4 to 1/4. So it is really like a spatial blob. But you see that this figure illustrates exactly the point that I made in the beginning, that no background is put into this. I mean, so space-time can form and be anything. And for arbitrary bare coupling constants, it has nothing to do with our world. But there is a certain range of coupling constants where it might be connected to our real four-dimensional world. So this is really an emergent symmetry. So, oops, yeah. But that's a coffee break afterwards. So, yes, but I'll soon be done. So anyway, here I show such a computer-generated thing where this is the 3 volume at the spatial slices, which is plotted up here, and this is time here. So here you see the blob, and this is a real configuration, and then you take the average of a couple of millions of these, and then you get this beautiful red curve, and here it is where also the error bars, the size of the error bars are measured, and you see that the expectation value it fits perfectly with cosine cube. If I were drawing a cosine cube curve here, you would not see the difference from the red curve. And this is exactly the spatial volume profile for some sphere, force sphere, if you use this metric here. So this is why we say that four-dimensional de Sitter-like space emerges. And the fluctuations, they scale like this. So the fluctuations, they scale like the square root of N4, while the, while the height here, it scales like N4 to the 3/4. So when we increase N4 for a fixed value of the coupling constant, then these fluctuations, they go away, and we get an infinite volume limit, but that's just an infinite volume limit. So we have obtained the goals declared in the beginning. We obtain an emergent geometry, and we can study fluctuations. And in fact, we can do much more. We can find an effective mini-superspace action and so on. I have no time to talk about that. But now let me relate it to continuum physics and the ultraviolet fixed point, because that was the purpose of this. So unfortunately, we don't have access in an easy way to some correlation links here. And this has to do with how to define two-point functions and all kinds of things like that. It's a long story, a very interesting story. I will not tell it. But we have to do something else then. So we, as a correlation length, not as a correlation, but as a length scale, we simply take the size of the system, so the size of our universe. And as an observable, I put it in quotation mark, we take this dimensionless coupling constant lambda times G. Now, if I use the simple functional randomization group truncation, in fact, the one first used by Martin Reuter when he calculated this, it is just the Einstein-Hilbert action, but with running coupling constants. And then if you take the classical solution to this and just do quadratic fluctuations around this, then you get that the fluctuations of V3 in the spatial slice divided by V3, it goes like the square root of this, and if you use these dimensionless coupling constants, it goes like this, where this K is the scale. This is the momentum cutoff. I know that functional normalization group people, they will not call it momentum cutoff, but still it's running to the, when it goes to infinity, this is the ultraviolet, and when it goes to 0, this is the infrared. So I will just call it momentum cutoff and identify it with our diffeomorphism invariant lattice cutoff in the following way. So here I just grabbed a figure from a recent article by Renata and Martin to show how this quantity behaves, how they imagine in the functional normalization group how it behaves. In the ultraviolet, it goes to the ultraviolet fixed point value, which is of order 1. And if you look at it, what it is today, it is quite small. So there is a huge growth there, and this is some approximate form which I described for this. There was a beautiful talk on Monday by Nobuyushi, where they actually calculated this this beta function, and it goes like this. So here is the ultraviolet fixed point. And you see, this is like this phi to the 4th theory ultraviolet fixed points which didn't exist, but here it seemingly exists. So, and then we find that the lattice spacing should go like this. Unfortunately, this is very small, so it's a huge factor here. So, but this is actually exactly what we measure. I mean, we are measuring this thing here, and we find an expression like this. And now, if this should stay constant, then n in 4 should go to infinity, then we would like, if there is an ultraviolet fixed point, then we would like this thing to stay constant. So the lattice spacing go to 0. It means that this coefficient that we measure in the fluctuations, it should go to infinity. But that's kind of natural that something like that should happen at a fixed point or at a phase transition, that the fluctuations should grow to infinity. So it is not, from this point of view, unlikely. So let us assume that we can find a fixed point where it diverges like this. Then this thing is constant if we can find, if we choose a path of n4 going to infinity, which compensates for this. So this can be checked directly by Monte Carlo simulation. So this is a thing we can do. Unfortunately, the results are a little bit inclusive because it requires very large volume. But in the case of our ultraviolet fixed point, then we would say the A scales to 0 like this, and this should be exactly the coefficient which is calculated in the normalization group approach. So here I've drawn the phase diagram again, and what we should see, what we can do is that we can follow a path like this towards this tentative ultraviolet fixed point where this is staying constant. So this is what the normalization group expect, that close to the ultraviolet fixed point, this should stay constant. So we follow this path, and this should lead us to this fixed point. So this is my last slide. So at the Monte Carlo simulations, we see that this indeed increases when we go this direction, at least by a factor 10. And moreover, whenever we can increase n4, it's not so easy, then we have been able to obtain more convincing signs that this is an ultraviolet fixed point. But it's not settled yet, I would say. Definitely not. But if it is, then we have a continuum limit where we can remove the cutoff. So just to give you, I'm done basically, but just to give you an idea of what we are talking about, because we are saying we are doing lattice simulations and so on, what kind of universes, what is the size of universe we are talking about? So the best we can do here is around 500,000 of n4s in the computer. I now put these guys in a hypercubic lattice, pack them in some way in a hypercubic lattice. How large is this hypercubic lattice? It is 10 to the 4th. So it's a small lattice. I mean, this is our universe. It's 10 to the 4th. So there is a limit to what we can expect to study in such a universe, which is just a lattice of 10 to the 4th, lattice spacings. And that's why I'm saying there are huge finite size effects still. What can maybe be a hope that what we see is good is that if you think about lattice computer simulations of Yang-Mills theory, the best result ever obtained in these simulations were the very first one by Michael Kreutz in 80 on a 4 by 4 by 4 by 4 lattice. Since then, the results has only got worse. Of course, I mean, today we laugh at his results, but nevertheless, he got everything right in a certain way. And so maybe even if our lattice is not larger than 10 by 10 by 10 by 10, still maybe it tells us some truths. But it is also clear that there's a limit to what we can study. I mean, there cannot be many black holes and so on embedded in such a lattice. I mean, so one cannot hope of studying this thing, but maybe one can hope of answering the question whether there is an ultraviolet fixed point. And that in itself, I think, would be quite interesting. Thank you very much for your patience.
Thank you very much, Jan. Let's have a quick question before we go for coffee. Yeah, wait.
Just because the session was about the causal structure, I like to hear a little bit of this story of how this started with being dynamical triangulations and it didn't have a causal structure embedded in, and then you didn't get this continuum limit, and suddenly, I mean, you changed radically your configurations, and then everything worked. If you can elaborate a little bit on that story.
Yeah, I can. Well, I can elaborate on it in the following sense that, strictly speaking, we have, of course, no idea what we get. So there are several steps here. I mean, so each triangulation starts out with a Lorentzian geometry, which is, of course, causal by construction. So that's fine. But then, as also kind of Christian remarked, then we sum over all possible triangulations which have different causal structures. So what the outcome of this is not so clear. But what we then do in addition, of course, which makes everything much more murky, is that we rotate to Euclidean space. So each of these configurations can be rotated to Euclidean space, so we can rotate back and forth there. But now we sum over all of these guys. As long as the sum is finite, we can rotate back. But but of course, in the infinite limit, rotation back and forth is a subtle thing. From a numerical point of view, it's not so easy to rotate back and forth. In fact, it's almost impossible. Terms which can be subleading in the Lorentzian can be important in the Euclidean. But this is known from ordinary quantum field theory also. I mean, there are something you can measure in the Euclidean lattice field theories in a good way, and something is almost impossible to extract unless you have some ingenious ideas like scattering amplitudes and so on. They do not come easy to you, but the Green functions you can measure there, and then you can say, okay, I know how to rotate my Euclidean Green function back to Minkowski space in flat space. This is the Osterwald-Schrader axioms that the Green functions, they are rotated back exactly in the right way. But here in gravity, of course, I'm afraid we don't know. Yeah.
Okay, so there is another question by Daniele, perhaps. And that will be the last question.
So thanks, Jan, for the talk. I haven't understood how you characterize the transition as a breaking of homogeneity and isotropy. Which observable do you use to characterize that?
Yeah, okay, thanks. Yeah. Well, that's very easy and naive, but probably correct. So on the other side of the phase transition, what is happening is that the geometry becomes kind of degenerated. So a single vertex gets an order which, if you move inside this, is of the order of N4. I mean, so the whole universe is centered around a single vertex or a single link of a very high order. So clearly such a situation, I mean, you don't have any homogeneity because everything is kind of linked to this vertex. That is what we say, just looking at it, extremely naively. While in the other phase, of course, you have distributions of order of vertices, but they're all continuous distributions, and we have seen nothing special happening. But of course, one has to quantify this. What do you mean by things being homogeneous? And isotropic. Of course, any individual triangulation is not homogeneous and isotropic, but just some arbitrary kind of triangulation. So some property of the average which we take should be satisfied. And this is exactly what Renate studied in the recent article, but you should ask her about how to define it better than just looking at this and say, oh, yeah, it looks pretty homogeneous. so that's how it is. Yeah. Yes.
Okay, thanks. So we'll have coffee now and start again at 11. Let's give Jan another round of applause.
20 minutes plus questions, is that good?
Yes. Yep, don't touch it. Okay, so please be seated, fasten your seatbelts. So let's get started with the next session of today. So I have two speakers, and we got creative, finding a nice catchy phrase to summarize these two talks. So the session will be on the field theory on and of space-time. We're kind of proud of that. And the first talk will primarily be on the on part, I believe, but hopefully this will navigate towards of at some point. So the first speaker is Kasia Reisner. She is a mathematician and physicist from the University of York and an expert on algebraic quantum field theory and renormalization. And she kindly agreed to give us a review on field theory on curved space-time, and a little bit of. Please take the floor.
Thank you. Thank you very much for this invitation. It's a great conference and a pleasure for me to be here. So as I told during the careers panel on Wednesday, depending on the audience, I'm a mathematician or a physicist. So depending on how you identify, if you're a mathematician, then I'm a physicist, and if you're a physicist, then I'm a mathematician. So don't blame me for not speaking the same language. Okay, so yeah, it's pretty much about QFT on curved spacetimes and similar. So I'm going to first tell you something about QFT, connections to quantum gravity, and how I think about it. It's going to be a very personal talk. It's really, my kind of view on the subject. That can differ from other people's views. So I'm not speaking for a community or even for my collaborators. So I'm just speaking for myself. Okay, cool. So yeah, so we're all after quantum gravity. This is great. And yesterday at dinner, it was mentioned that, well, if it takes not too long to find it, then we will not have those wonderful conferences. So it's always the experience of getting there, which is fun. And I'm happy to join it. So this is something that people tried in quantum field theory after Young-Mills was quantized, and actually even before, people felt good about this. So how do you quantize gravity? Well, it's a field theory. So you take a metric G, you perturb it by something, and yeah, what can go wrong, right? It's great. So here is when people mention that there are potential problems. So the theory is power counting non-renormalizable. So predictability is a bit of an issue. So there are two ways out, which are very much interconnected in my head somehow. So there's effective theory approach. So you can think of effective theory of quantum gravity, where you don't care about the fact that you don't have a UV completion, okay? We can still calculate things. We can still calculate corrections to classical gravity effects, and see if something can be measured experimentally. Or we can look for different fixed points, so non-Gaussian fixed point, and there was a lot said about asymptotic safety program, so I'm not going to review it yet again, so it's freshly in your head. Here I mentioned some names of people which is far from being complete. I'm just essentially thinking about stuff that inspired me personally, and people I've talked to about these things. Okay, but what if we are completely wrong with this field theory idea? What if space-time is fundamentally discrete? Then this field theory stuff is just an approximation. Jan talked about one approach there, so causal dynamical triangulations. I actually kind of joined a slightly different crowd in pursuit of discrete fundamental structures of spacetime, which is the causal set community. And in fact, you know, in a sort of trying to bridge quantum field theory on curved spacetimes with causal sets, you might be interested in doing QFT on causal sets. And this is something doable, and several people are working on that, and some of them are hopefully in this room, unless they left. Hi. But this is another connection between quantum field theory and quantum gravity. Okay, and there are some things, you know, with all these well, approaches that you might want to think about independently of approach, which are, well, first, Lorentzian signature. Somehow, you know, these guys would feel best in Lorentzian because, well, somehow in curved spacetimes, this is typically how you work.
today's afternoon session. So our first speaker is going to be Saeed Raskou, who will tell us about the problem of time in quantum cosmology with a quantum clock.
No, okay, great. So yeah, so this is a work with Rodolfo Gambini in collaboration with Rodolfo Gambini and my PhD student Jordan Roberts. The title is a little bit misleading, so you will see why. So I'll talk about the problem of time in general, conditional probabilities, and our model, and finally the result, which is under construction. So you have heard about problem of time during the conference, but let me just give you a reminder of what it is. The fastest way to see this is in the classical regime is we have in theories of nature, especially fundamental interactions, we have this relation between canonical variables, which are bound to be equal to 0, and these are called constraints. A class of these constraints are called first-class constraints, and those are the ones that generate gauge transformations in the sense that if you choose any function of the phase space f, and you put that in Poisson bracket with this constraint, you get something delta f, and that's the gauge transformation of f under this first-class constraint. Now, all good until now. Now we can also define Dirac observables, which are naturally observables are things that don't change under gauge transformations. So we have a gauge transformation of these observables. These are defined by their gauge transformation being equal to 0. So that means that their Poisson bracket with the first-class constraint is 0. Everything until now looks nice. Now the problem arises here. So the Hamiltonian of the full gravity, or the full gravity plus matter, is a constraint, or combination of first-class constraints. So when you want to compute the time derivative of Dirac observables, so these are observables, it means that that's the normal way of computing the time derivative or evolution. It turns out because of by definition, their time evolution, because this is a first-class constraint, is their gauge transformation. So time evolution is just gauge transformation. It's not physical. In other words, it's just 0. So all the constants, all the observables, Dirac observables, are constants of motion. So everything is frozen. That's called the problem of time. This is the easiest way to see that. In the quantum regime, all the physical states should be destroyed by all the first-class constraints. Hamiltonian is the first-class constraint. It should destroy the states. This means that you don't get a Schrödinger equation, which on the right-hand side you get this time evolution. You only get 0, so it means that, again, you have a frozen framework for your system. So this is the sense of a problem of time. Now, how you solve this, there are several ways to do that. There's a very nice review by Kukash, I think 2011. The one I like and I'm working on is the conditional probability interpretation. And what it tells you is that, suppose that, so basically I can ask probabilistic questions. And suppose that I create or basically construct a variable called t, I call it clock, out of canonical variables. I construct another variable q. This is the system or what I want to find its evolution with respect to this clock variable. I construct that one too. And then I ask the question, what is the probability of q taking value q naught, given that t has already taken the value t naught? So this is the conditional probability. And it is written as the joint probability of p q naught and t naught divided by the probability of t naught. Okay, so it is the classical version. In the quantum version, what you do is that you have a Hilbert space of clock, the cross product Hilbert space of clock and the other variable, and you construct these projection operators. Well, so you have a density operator for your system. You construct these projection operators, for example, for t, for clock being equal to t naught. And you also construct another one for q. And then you ask the question, so if I act this on my basically state, if the answer of if the action gives you the condition that, yes, the eigenvalue of t is t naught, then you go to the next step and say that, okay, now is the eigenvalue of q is equal to q naught, and if that answer is yes, then you get something non-vanishing, and it gives you a probability divided by this one. So that works based on these projections. Okay, so this thing, people in in quantum mechanics like to write it in another way. They just use the property of projection operators. You write it like that, and finally, they use, this is very important, they use the fact that these projection operators in their formulation commute, and then they write this, because they like this part, they call this a new sort of density operator, they call it, well, it has different names, but you see that this term for them is important. But this is a condition where operators corresponding to